On July 21st, 2023, at NASA's Deep Space Network Station in Canberra, Australia, the signal from Voyager 2 simply stopped. Not faded, not weakened, stopped. A spacecraft over 12 billion miles from Earth, the only human-made object in that entire region of the galaxy, had gone completely silent, and for several days, nobody at NASA's Jet Propulsion Laboratory knew if they would ever hear from it again. What caused that silence, and what Voyager 2 had already been quietly recording in the months and years leading up to it, is a story that genuinely unsettled the scientists who spent their careers on this mission. Not because of anything supernatural, because of something far more grounded, and in its own way, far more concerning. Real data suggesting that the invisible shield protecting our entire solar system may not be as reliable as we assumed. Let's start with what actually happened that July, because the sequence of events alone is enough to make you understand just how little room for error exists on a spacecraft this old, this far away. Routine commands are sent to Voyager 2 every so often, small instructions to calibrate instruments, adjust settings, keep the decades-old spacecraft running as efficiently as possible. On this occasion, a scheduled sequence of commands, meant to make a minor adjustment, accidentally caused Voyager 2's high-gain antenna, the dish responsible for keeping its signal precisely aimed at Earth across billions of miles of empty space, to tilt just 2 degrees off target. 2 degrees. That number is almost comically small, the kind of margin that sounds trivial in any ordinary engineering context. But at a distance of 12 billion miles, 2 degrees of misalignment is more than enough to send a signal missing Earth entirely, vanishing into the surrounding dark instead of reaching the massive radio dishes waiting to receive it. For engineers at JPL, this was about as serious as a problem gets, because Voyager 2 has no backup transmitter, no redundant antenna, nothing to fall back on if the primary system loses its lock on home. Every single system aboard both Voyager spacecraft has, over the decades, been stripped down to bare essentials to conserve power, and that includes any real redundancy. What you have left, after nearly 50 years, is one antenna, one transmitter, one shot. And because Voyager 2 sits so far away, any command sent from Earth to correct the problem takes over 18 hours just to arrive, with the spacecraft's response taking another 18 hours to come back, assuming it can be received at all. A single attempt to fix the problem and confirm whether it worked takes the better part of 2 full days. Mission engineers describe the ensuing period in blunt terms. They had lost contact, and they genuinely didn't know if they were about to lose the spacecraft permanently. What happened next has become something close to mission legend inside JPL. Rather than simply wait and hope the antenna would happen to drift back into position on its own, engineers made an unusual decision. They used the Deep Space Network's most powerful transmitter, a system normally reserved for far closer, far more routine targets, to send an extraordinarily powerful brute force command toward Voyager 2's last known position, essentially shouting in its general direction as loud as physically possible, and hoping the spacecraft's own systems would pick it up despite the antenna misalignment. It became known internally, half-jokingly and half in genuine relief, as the interstellar shout. And, against real odds, it worked. Within about 2 days, a faint carrier signal, a bare, minimal heartbeat, came back. Voyager 2 was alive. The antenna gradually corrected itself as part of its normal reorientation routine, and full communication resumed not long after. But for those few days, the mission had come as close as it ever had to simply losing one of its 2 remaining active spacecraft to a 2-degree accident, permanently, without warning, and without any real way to intervene fast enough to stop it. That close call, on its own, would be enough to unsettle anyone who understands just how thin the margin for error has become on a 49-year-old spacecraft with almost nothing left in reserve. It wasn't even the first time Voyager 2 had gone quiet without warning. Back on January 25th, 2020, a routine maneuver triggered the spacecraft's automated fault protection system, a built-in safeguard designed to shut down non-essential systems the moment onboard power or attitude readings drift outside expected limits. All 5 of Voyager 2's active science instruments powered down automatically, mid-mission, without any human decision behind it, simply because the spacecraft's own programming judged that survival mattered more than data collection in that moment. It took engineers roughly a week of careful, patient work, sending commands across that same maddening multi-day round trip, to confirm the spacecraft was stable and begin bringing its instruments safely back online. By early March of that year, Voyager 2 had returned to full, normal science operations, but the incident was a stark reminder that even routine actions now carry real risk on a machine this fragile. But neither of those incidents, serious as they were, is actually the part of this story that has scientists most quietly concerned. That part comes from something less dramatic on the surface, and far more significant underneath, what Voyager 2 has been steadily measuring since the moment it crossed into interstellar space in the first place. In November of 2018, Voyager 2 became the second human-made object in history to leave the heliosphere, the vast magnetic bubble generated by our sun that envelops the planets and shields us from the harshest radiation the galaxy has to offer. Unlike its twin, Voyager 1, whose plasma instrument had failed decades earlier, back in 1980, Voyager 2 still had a fully working plasma science experiment on board, giving scientists a direct, unambiguous measurement of the transition the moment it happened. That distinction matters enormously. When Voyager 1 crossed the same kind of boundary 6 years earlier, scientists had to infer the crossing indirectly, watching cosmic ray levels climb and heliospheric particle counts fall, piecing together a picture from secondary evidence, because the one instrument built specifically to measure the transition directly had already died decades before the spacecraft got there. Voyager 2 didn't have that problem. Its plasma instrument recorded the moment cleanly, in real time, showing the solar wind particles around the spacecraft dropping essentially to zero within less than a day, replaced by the colder, denser material of true interstellar space. And what that instrument found once Voyager 2 was fully immersed in that environment added real, direct weight to something Voyager 1 had only hinted at years earlier through less certain means. The plasma surrounding both spacecraft, once they left the heliosphere, turned out to be significantly denser than pre-crossing models had predicted, not by a small margin. By enough that scientists had to seriously reconsider what the boundary of our solar system is actually doing to the material passing through it. The leading explanation is that plasma gets compressed right at the edge of the heliosphere, piling up in a zone where the outward push of the solar wind meets the inward pressure of the surrounding interstellar medium, similar to the way snow piles up in front of a plow blade rather than simply being pushed evenly out of the way. Voyager 2's data confirmed that this compressed, higher density plasma isn't a fluke limited to the one location where Voyager 1 happened to cross. It appears in a completely different part of the boundary, in a different hemisphere, at a different point in the sun's activity cycle, which tells researchers this compression effect is a genuine structural feature of how our heliosphere interacts with the wider galaxy, not a one-off anomaly. Confirming that compression is real and understanding exactly how strong and how consistent it is matters for a very concrete reason. The density and behavior of the material just outside our solar system directly affects how much galactic cosmic radiation, the high-energy particles flung outward by ancient supernovae across the galaxy over millions of years, actually makes it through to us. Here's the part that carries real weight, and it's not speculation. It's documented physics built directly from Voyager's own instruments. Voyager 1 discovered that the heliosphere blocks more than 70% of that incoming galactic radiation from ever reaching the inner solar system, including Earth. That protection isn't automatic, and it isn't guaranteed to stay constant. It depends on the size, shape, and strength of the heliosphere at any given moment, and that in turn depends on the sun's roughly 11-year activity cycle, along with whatever structures the solar system happens to be moving through in interstellar space at the time. Scientists studying Voyager's readings have found that the boundary itself appears to be dynamic rather than fixed, contracting and expanding, thinning in places, over timescales far shorter than anyone assumed when the mission first began. Voyager 2's own crossing actually happened faster and cleaner than Voyager 1's, taking less than a day compared to nearly a month for its twin, a difference researchers now believe may be tied to the heliopause itself physically moving inward at that particular moment, effectively meeting the spacecraft part-way rather than staying fixed in place while Voyager 2 simply passed through it. If the edge of our solar system can shift measurably over the span of a single solar cycle, contracting and expanding almost like something breathing, then the amount of protection Earth receives from deep space radiation at any given moment is not the stable constant that older models assumed it to be. If our solar system's shield against cosmic radiation isn't the fixed, stable structure earlier models assumed, that has implications well beyond academic interest. Cosmic radiation exposure is a serious, practical concern for any future long-duration human spaceflight beyond low Earth orbit, a real and active area of research for agencies planning crewed missions to Mars and beyond, where astronauts would spend months or years outside the added protection of Earth's own magnetic field. It also plays a role in atmospheric chemistry here on Earth, since incoming cosmic rays are known to interact with cloud formation and upper atmosphere processes in ways scientists are still working to fully quantify, with some research suggesting a connection between cosmic ray flux and long-term climate patterns, though that link remains an active and still debated area of study rather than settled fact. A weaker, more variable heliosphere doesn't mean sudden danger to anyone reading this today. It means our working assumptions about how well protected we are, assumptions built largely from remote observation before Voyager ever got out there to check directly, may need real, careful revision based on measurements no instrument before this mission had ever been in a position to take. This is where honest science, not sensational claims, is what actually deserves your attention, especially given how much noise surrounds this particular spacecraft online. There's no credible evidence of any anomalous, structured signal suggesting contact with anything intelligent, despite what a number of viral posts and videos have claimed in the past year, some citing anonymous leaked JPL reports or unnamed SETI researchers that don't appear anywhere in actual NASA communications or peer-reviewed literature. NASA has been transparent about every genuine hiccup in Voyager 2's long life. The 2020 fault protection shutdown that briefly powered down its instruments as a safety precaution, the 2023 antenna mispointing that nearly cost the mission its connection permanently, both fully explained, fully documented in public mission updates, and fully resolved through ordinary, if nerve-wracking, engineering work carried out across billions of miles and multi-day communication delays. What makes this story worth telling isn't a mystery signal from something unknown. It's the quieter, more sobering discovery sitting underneath all of it, that the boundary protecting our entire solar system from the radiation of the wider galaxy is thinner, more dynamic, and less predictable than the models built before Voyager ever crossed it. There's also something worth understanding about just how precarious the ongoing operation of this spacecraft has become, because it adds real context to why every single transmission still matters so much. Voyager 2, like its twin, runs on a radioisotope thermoelectric generator, a nuclear battery converting the heat of decaying plutonium into electricity, and that power supply has been shrinking steadily since launch, losing a small but unrecoverable amount of wattage every single year. To keep the spacecraft's remaining instruments alive as long as possible, NASA engineers have had to shut down individual systems permanently over the years, instrument by instrument, trading scientific capability for extended survival. Voyager 2 currently operates with just a handful of instruments still active, a fraction of what it carried at launch in 1977. And every additional year of operation is the product of increasingly difficult power budget decisions made by a team fully aware that there is no way to send a repair mission, no way to swap in a fresh part, no safety net of any kind, 20 billion kilometers from home. Voyager 2 is currently more than 20 billion kilometers from Earth, moving through the same turbulent, structured interstellar environment its twin has been sampling since 2012. Both spacecraft are down to a handful of working instruments. Both are operating on power supplies that lose a few watts every single year, and both are being kept alive through increasingly difficult engineering decisions made by a team working with an 18-hour communication delay in each direction, meaning any single mistake, any misjudged command, any unexpected drop in power could take days just to properly diagnose, let alone fix. Every transmission that does arrive, faint, slow, and real, adds another data point to a picture. Scientists are still assembling. A picture of a protective bubble around our home that is not static, not guaranteed, and not fully understood, even after nearly 50 years of direct measurement from the only two instruments humanity has ever managed to place beyond it. That's the actual warning buried in Voyager 2's data, if you want to call it that. Not a message from something out there reaching back toward us, and not evidence of contact with anything intelligent, however dramatic that story might sound. A quiet, patient reminder from our own instruments, built by engineers in the 1970s who could never have anticipated any of this, that the shield we've always assumed was solid, permanent, and unchanging, is actually something more fragile, more active, and more genuinely worth understanding than we ever gave it credit for. The most important thing Voyager 2 has sent back isn't a mystery. It's a fact, hard-won across billions of miles and nearly 5 decades, that the edge of our solar system is alive with structure and change in ways that only direct measurement, not assumption, could ever have revealed.